Okay, so welcome to our Heliocon seminar series. Heliocon is a 5-year research effort led by NREL partnering with Sandia and ASTRI and DOE CETO office to develop and manage a national laboratory-led US consortium to support research, development, validation, commercialization, and deployment of low-cost heliostats for concentrating solar power and solar thermal applications. So this seminar is put on by the Resource Training and Education topic. And a few things before we get started. This is being recorded and will be made available afterwards on the NREL YouTube channel. Please stay on mute when you are not talking. We'll have some time for Q&A at the end of this where you'll be able to unmute yourself and ask your questions directly. You can also use the chat to ask questions. So feel free to put questions in the chat during the presentation, and we'll make sure that we get to those when Parthiv gets to the end of his presentation. So with that, I'll go ahead and introduce our speaker, Mr. Parthiv Kurup, CSP Cost and Systems Analyst, provides objective analysis for guiding CSP investment decisions. He has led the CSP bottom-up analyses for parabolic troughs and heliostats. He works on techno-economic analysis, cost modeling, supply chain, and manufacturing analysis. Subject areas of interest and expertise include CSP, renewable thermal energy systems for process heat, and advanced manufacturing processes. All right, with that, Parthiv, if you want to go ahead and get started.
Great, thanks, Rebecca. I have the pleasure of giving a seminar today, a short one on some of the recent bottom-up analysis for heliostat collectors and also the initial analysis on the heliostat supply chain. I'm expecting to keep it about 40 minutes or so. So the first section is really focused on the bottom-up analysis. And it's important to highlight right at the beginning that this report is public. Please, go to the link and you can then go into much more detail. As an overall, the two main heliostats have been picked for the analysis, for the bottom-up analysis. The first is the SCHLEICH, Bergermann and Partner, or SBP Stellio, and the Solar Dynamics SunRing heliostats. Now, in the process, we did approach quite a few developers and then also get a significant amount of data to be able to get to this point. But developers also included BrightSource, Vast Solar, and Heliocon, who were also part of the selection process prior to the first two being selected. An important tool that I'll mention now and then come back to is something called Design for Manufacture and Assembly. And that was really a key piece for the analysis to be able to figure out manufacturing costs, for example. And right at the beginning, it's important to highlight that the amount of heliostat area or the aperture area is about 1.1 million meters squared for both of the modeled cases. Starting with the commercial heliostat, or what was considered the commercial heliostat, the Stellio, it has been designed and developed in a consortium, primarily through European developers and research institutes. And within 5 years, this heliostat has actually gone from testing and development into the field itself. So for example, right now, it is deployed at the Hami Chinese CSP power tower plant in the Xinjiang province near Mongolia. It's a 50 megawatt electric plant with 8 hours of molten salt storage, operational for the last few years. And even in the process of installing it, it has already been optimized for that site and conditions. So for example, you'll notice that in the picture below, the heliostat facets do not have a hole in the center. That's why it went, for example, from 48 meters, it went from 47.5 meters squared to 48.5 meters squared. They actually found it was pretty cheap to do that as a fix. The Hami field, for example, is about 700,000 meters squared of aperture area and about 14,000 heliostats. within the implementation phase of the HAMI field, they actually changed the design from foundations into concrete pilings, which already helped reduce cost as well. This design is also being deployed at the Redstone CSP plant in South Africa. That is a 100 megawatt CSP power tower plant with 12 hours of storage. The developer is Aqua Power, and in the region of South Africa, it's in the Northern Cape province. When we look at the design for the Stellio, it's quite a novel design because of its pentagonal shape, for example. And the image you're seeing shows the back face of the structure and the linear actuators, for example. It's a steel frame design, and the foundation, as I mentioned, can either be steel and concrete or driven piles, for example. In the current analysis, when you look at the Stellio, you're looking at 4 millimeter glass, and each heliostat has an approximate aperture area of about 48.5 meters squared. In the field, for this large million meter squared heliostat field, it's about 22,239 heliostats. And so when you look at the design and the shape, again, it's very interesting and very novel. Similarly, the advanced design, the other design that's compared or used in the analysis is the SunRing from Solar Dynamics. And as you can see, this is a more standard rectangular design, and it's actually the evolution of the Abengoa ring of power design. And so this design incorporates an increased aperture area, improved structure and stiffness compared to that. It has a simpler facet design, and for example, as you can see in the image, there's actually a PV panel which also helps control the movement as well. For the analysis, again, 4 millimeter glass is used, and compared to the Stellio, these are actually 27 meters squared instead of about 48.5 meters squared per heliostat, and there are 40,000 of these in the field, leading to approximately, again, 1 million meter, approximately 1 million meters squared. The similarity also between the two designs is also that both are significant users of steel, and that'll come out actually in some of the analysis later as well. As part of the methodology for the analysis, it's important to mention both the tools and how it's been used. So Design for Manufacturing and Assembly, DFMA, is an industrial software tool developed by Boothroyd Dewhurst, and it's really incredible for what it can do in terms of the manufacturing and the assembly costs for components and then subcomponents as well. NREL has utilized DFMA for other technologies as well, such as small hydropower, modular thermal energy storage, geothermal turbines, and also advanced metal extrusions. The links will be, you can go to the reports on those designs as well. DFMA is made up of two main parts, so design for manufacturing and design for assembly. And so design for manufacturing is built upon detailed databases of material properties and machine capabilities, which then allows the knowledgeable user to calculate the primary manufacturing cost for every single component and then assemble that into an overall product. It really comes up with something called a should cost. And that should cost will be based on the material, the process steps, the manufacturing, the setup time, the tooling investment if needed. So for example, clearly a low carbon steel would have a lower dollar per pound cost than a high carbon steel, for example, or a tooling steel. In DFM, it has the ability to input CAD models as the basis for geometric consideration. Now, you can do it without that as well, but certainly can be done and makes the process more straightforward. Every component that we could analyze from a manufacturing perspective, this is typically the metal component, has been done for commercial scale manufacturing with a manufacturing facility that can manufacture those types of parts. And things like the purchase parts, which we'll see later on, will actually, we have quotes for those. And for specialist components like the mirror panels, for example. There are also tooling investments which come in for certain parts depending on if certain processes are used as well. In the design for assembly, you can then take these individual component parts and then start building subassemblies or welding certain parts together to be able to get larger subassemblies, and then develop the assembly cost associated in the manufacturing facility. That's important to mention. So when we look at the manufacturing, the methodology from manufacturing up to construction and install costs, it's really important that the bill of materials is incredibly detailed. And so the bill of materials starts from the design, incorporating then CAD models, then specific numbers of components per heliostat, and then of course multiplied for the number of heliostats for the field. And as such, in the bill of materials, we would want to include all the metal components, of course, then mirrors and drives and fasteners, for example, in the purchase parts, and then working up to next level of assembly and also construction. For both designs, we did get significant amount of support from the manufacturers and developers to determine what their estimated estimated construction cost could be for that size of plant, and also what sort of site assembly facility would be needed. And eventually we come to an installed cost, which includes the manufacturing, the subassembly, the purchase, the construction, and then field costs as well. So for example, DFM can be used to show the effect of volume over time, and also the process chosen. So for example, on the left, you can see the CAD model of the solar dynamics actuator arm. That's one of the arm plates as an input into DFM. And then based upon the process picked, so for example, you could pick stamping, you could pick laser cutting, for example, and then on the right, you can see the cost versus life volume. So for example, as the life volume of the stamping process increases from 1 to 1,000 to 100,000 and more, you can see that the cost effectively starts leveling out. And at the production volume that we were estimating, the should cost is pretty much the lowest it's going to be. And that incorporates the tooling investment, not the machine, but the tooling investment for the stamping process. So when we come to the Stellio and the results, again, this breakdown and other breakdowns can be found in the report, but the estimated installed cost chart on the right shows the same breakdown, but by categories such as purchase parts and manufacturing parts, site labor and so on. It's important to mention designed for large scale deployment, 1 million meters squared and above. So for example, it has an associated $7.5 million assembly facility, which would need to be built next to the construction site. When you look at some of the key cost areas for the Stellio, we found that things like the assembly and the structures were about 15.7%, and mirrors actually were about 13.4%. When you break it down by category, It's approximately 44% on purchased parts. So for example, rivets, fasteners, mirrors, drives, and around 31% on the manufactured parts, like the arm components and the frame, for example. Again, this leads to about a $127 per meter squared installed cost. When the same is done for the SunRing for solar dynamics, we found that the installed cost was closer to $96 per meter squared. Now, it is important to mention that the SunRing at present has not been deployed at scale at this scale. So this is a comparison and modeling perspective. But from that perspective, for about a 1 million meter squared field and 40,000 heliostats, we found that it was approximately $96 per meter squared. And an image of the, so actually the real, let's say the hard prototype can be seen in the image on the right. When you look at the SunRing, for example, and the purchase components compared to other designs, it's very clear that there was a heavy increase in purchase parts. So for example, 56% on purchased parts and only 28% on manufactured parts. So the design philosophy is more structured around off-the-shelf, large volume, very specific, highly scalable parts, for example. When you look at some of the largest contributions, the drives are a very significant portion of the design, and also the mirrors. So about 16% each. The assembly itself and the back structures and such about 11%. So in the report, you'll find much more detail on this. But we also did some analysis to show what would the impact of changing the CapEx or the capital expenditure of the heliostat field for the effect on levelized cost of electricity within the SAM or the system advisor model. So for example, starting from a default case of about 1 million meters squared of aperture area and $150 of it leads to about $151 million default case. Comparing that to the analysis of a commercial and the advanced situation, the CapEx of the field is about 137 million or about 107 million if it can be realized. So effectively a 9% or 29% reduction from the default scenario. This has quite significant levelized cost of electricity impacts as well. So for example, when we looked at two, the first being Tucson, Arizona, and the second being Daggett, California, the default case, so for example, utilizing the prior value of the installed cost in SAM leads to about $94 per meter squared. But it's important to mention that this is specifically with the 26% ITC. It's expected that that would be in place for any new plants in the US. And so comparatively, the levelized cost of electricity for the commercial and advanced cases is about 92 and about 96. These are, of course, estimates and based upon the financials used. But as you can see, again, there is a pretty good impact from reducing the cost of the solar field on the overall levelized cost of electricity. The same in Daggett, California, for example, the default is around $92 per megawatt hour based upon, of course, the resource and the solar conditions in Daggett. And then similarly, a levelized cost of electricity for the commercial and advanced cases was about $89 and $83 per meter squared. And again, I would suggest going to the report because that has all the details in there as well. Now, relative to the two designs, it's important to highlight some of the insights and some of the cost reduction mechanisms as well. So for example, the Stellio was designed and developed in a consortium effort. So for example, it connected research. So this is the DLR, or the Deutsches Luftraumfahrt, or the German aerospace division, industry. So for example, Inge Metall and Zurich, and also the developer SBP itself. And that was key in really helping develop this, this collaborative, now public or commercial heliostat. So for example, in the installation itself of the Hami field in China, it was already found that the original design of the concrete foundations could be reduced significantly if you were able to use driven piles instead. So at Hami, information from the developer showed about a 20% reduction in the field cost. And now this specific technique is being deployed at the Redstone Heliostat field in South Africa, which is in construction at the moment. DLR analysis has found that the Stellio has further cost reduction potential up to maybe $103 per meter squared in, let's say, 2016 dollars, which could be a little higher based upon steel costs today. But the key drivers, or the key developments for the Stellio from now until 2025 include things like a reduction in site preparation, such as the driven pylons as mentioned, or earth screws. That has a very significant impact. Another key area is the improvement of maintenance programs and using closed loop control. DLR found that that could reduce another 25%. When structure costs are looked at, that has a significant effect. So for example, if thinner materials can be used, increasing automation, very key drivers, which could help reduce cost. And then the last point on the growth of the heliostat competitive market. So for example, if you could see development and deployment in significant quantities of the Stellio, that could have significant benefit as well, up to a 35% cost reduction. I've provided the link to the paper as well, if for interest. Similarly, the SunRing from Solar Dynamics also has certain design criteria and design preferences as well. So for example, the ring of power concept was taken forward in the SunRing, which has allowed it to become a larger heliostat with a very similar design philosophy. And the design philosophy is really focused on off-the-shelf components, large volumes of manufactured parts, to be able to help these cost reductions through high-volume precision manufacturing. The SunRing that was modeled was also with 6 helical piles, and of course that can change. So for example, you could use earth screws or driven piles, again, depending on the ground conditions. And things like the large flat mirrored surfaces help with the assembly and the tolerances needed for that side of it. Now, it is important to mention that at present, the Solar Dynamics SunRing has not been deployed at scale, but it is, we are working with Solar Dynamics to understand real costs if and when that occurs. So for example, looking at some of the design aspects of heliostat, this slide is actually from a peer of mine, Jeremy Sment, but it's really interesting to show and see this type of perspective. So in terms of cost analysis and the design impact, there's potentially about a $33 per meter squared saving if, for example, some of the cost realizations can be made. So for example, things like labor has a cost reduction, things like the assemblies and the base structure can have pretty good potential cost reduction through the use of a different design. And this type of work really can help feed into the Heliocon roadmap, which will be needed to be able to meet DOE sunshot targets, for example. In summary, the report can be found at the NREL link. And again, the major result was, let's say, the estimated heliostat installed cost at $127 per meter squared, and the advanced heliostat at around $96 per meter squared when realized. And some of the uses of this is that, so for example, the $127 per meter squared feeds into the annual technology baseline, the ATB 22, to then help with the cost projections into the future. This type of analysis, of course, also feeds into the supply chain analysis, which I'll highlight next. And this type of key bottom-up analysis really shows the design and development perspective towards $75 per meter squared and even $50 per meter squared. As part of this seminar, it's also worth mentioning the current analysis on the supply chain for heliostat supply chain in the US. And so it is important to mention that this supply chain analysis is part of the Heliocon Advanced Manufacturing, or Task 4. It's also important to mention that this report is in review right now and will be published shortly. So in summary, as an overall, the heliostat supply chain is made up of pretty readily available commodity materials such as steel, aluminum, and glass. An important finding we did find is that there is a lack of a US near-term market, which could be a challenge, obviously, for domestic heliostat manufacturers for electricity generation, at least. There is potential in the near to midterm in China, Africa, Middle East, for example, in the next couple of years. Within the US itself, if CSP can start hitting cost targets and reduce in cost over time, there is the potential for several gigawatts of CSP deployment for electricity, particularly power tower, and potentially a significant amount of jobs as well. So again, when this report is published, you'll be able to see this in greater detail, but I wanted to provide a snapshot of some of the analysis. So here, for example, this is the material content analysis, and in the metric ton column, you're seeing the amount, the metric ton effectively, of that material, so glass, steel, for a heliostat field of about 1 million meters squared. And so you then compare that with the annual production of that commodity material in the US. So for example, in 2020, glass in the US has about a 20 million metric ton capacity. Therefore, you can figure out how much of the US production would be utilized in producing one heliostat field, for example. And then it leads to an estimated market value of the amount of commodity material used in the commercial design and the advanced design, and similarly in the steel case for the commercial and advanced as well. So from this type of material content analysis, you can find out or estimate jobs potentially linked with one heliostat, so for one heliostat field. So for example, comparing it to prior analysis in 2015, we can see that the amount of direct and indirect jobs relative to earlier was about the same. But for example, when we look at the glass side, the number of jobs does change, for example, slightly compared to prior design. So here we're looking at the, let's say, direct and indirect jobs for one heliostat field. So for example, in the commercial design, let's say in the US, we estimated around 94 jobs could be created and utilized based upon the market and the size of, let's say, the glass industry in the US. So In the US in 2020, about 87,000 jobs, 88,000 jobs were associated. And so you can work out how many jobs could be associated with a field. When you look at it from one field to, let's say, 100 fields to 1,000 fields, then the numbers of jobs become much larger. So, for example, for 100 heliostat fields, which could be about the equivalent of, let's say, 10 gigawatts of CSP in the US, there could be an associated, let's say, 10,000 jobs or 9,500 jobs in the glass sector, and about 8,000 jobs in the steel sector. Again, these are estimates based upon the design that's chosen. And then, of course, if you can hit 100 gigawatts of CSP in the US, just in the glass industry and just in the steel industry, there could be a utilization of about 67 to about 95,000 jobs, which is huge. As part of this analysis, and also analysis that's been done by NREL and other labs, the solar future study is a really key potential outlook of what solar could do for the US. And the numbers shown in the table are related to PV. So the gigawatts of solar PV deployed from, let's say, now until 2035 and then 2050. And there are three main scenarios which are of importance. The reference scenario, where in today's conditions, things are improving and being deployed, in a decarbonization scenario where 95% of the grid is effectively decarbonized relative to prior baselines, and then the decarbonization plus electrification scenario where even more is required. So when you look at the emissions reductions targets and potential, even in the reference scenario, there is an expectation there could be a 45% reduction in emissions using solar PV and wind at the current rates of deployment. But if, let's say, the decarbonization scenario can be hit, let's say a 95% reduction in emissions could occur through solar PV and wind, for example. This, of course, has a phenomenal impact on the deployment of PV. So, for example, looking specifically at PV, this could be between 670 to up to a gigawatt, depending on how aggressive and how low the costs get for PV, and including battery scenarios as well. This then has the impact of both direct and indirect jobs of between 500,000 and potentially even 1 million. And so, again, the links are provided for the solar future study on the side. The solar future study also takes into account the deployment perspective of CSP for the electricity market from now until 2035 and 2050 as well. So the estimates find about 39 gigawatts could be deployed in the US, and depending on how aggressive the cost targets are and how well CSP could meet some of the cost targets set by CEDO, the deployment could range potentially from 35 gigawatts to 158 gigawatts. Of course, that's on today's cost structures and markets in the US. So in the Heliostat supply chain analysis, we also looked at some of the impact on the annual technology baseline. So the ATB 2022 has utilized some of the cost data that we found in the original Heliostat analysis, the bottom-up analysis, and also it's then reported in the Heliostat supply chain analysis. So the ATB 2022, which is being finalized and will be released shortly, uses 2020 as the start point. And so so in 2020, the estimated CSP overnight cost of capital, or the OCC, without additions for things like finance costs, was around $6,242 per kilowatt electric. And of course, that includes the turbine, the storage, and the solar field capital cost components as well. By 2035, in the moderate scenario, based upon literature projections and based upon how the NREL mid projection has been shown and done, the estimates are around $4,069 per kilowatt, going down to perhaps $3,100 per kilowatt electric in the advanced low-cost scenario. And similarly, for the moderate, assuming deployment, assuming costs can be really reduced over time, the current projections estimate or give an estimate of about $3,750 per kilowatt electric, or about $2,761 for the advanced scenario. Of course, this implies that all three things like the turbine storage and field costs would reduce or could reduce significantly. And of course, the heliostats are a significant portion of the cost driver for the future. When the supply chain in the US is looked at, and also globally for heliostats, there are some key challenges that really need to be addressed and also overcome. So for example, one of the key challenges is that heliostats, of course, are complex parts and structures, but there is a scale associated with manufacturing them to be able to get cost reductions. A really key challenge for heliostat manufacturing, and also for not only in the US, but also outside, is the inconsistent demand pipeline. It's really critical that a consistent pipeline exists where manufacturers know that they can supply into markets, supply into projects that are being built. So for example, if you have the situation like currently where you have start, stop, and huge ramp ups in production and then ramp down, it's going to lead to large difficulties and in establishing the supply chain as well. Of course, we've lived through the last few years, and global supply chain disruptions have affected all parts of commodities, but also transport and also components. So that's a significant challenge, short-term challenge, which is present in pretty much all markets as well. And as I mentioned at the beginning, there are some pretty uncertain US, let's say, perspectives on the pipeline and also the amount of CSP that could be deployed in the next 3 years or the next 5 years, which then helps spur the manufacturing perspective. When you look at it from the opportunities, though, there are significant opportunities for heliostat manufacturing, both in the US and globally as well. So for example, as mentioned, there are near-term markets like China and Morocco, UAE, which are deploying CSP. And so that type of deployment of CSP and deployment of heliostats will help strengthen both suppliers and improving the ability to get components at scale. Of course, within the US, there is a strong innovation environment which can be leveraged to be able to utilize, to be able to lead to cost reductions for heliostats. And heliostats don't necessarily have to be used for just the CSP for electricity markets. There is significant potential to use them for the process heat market, like, for example, Heliogen is doing currently. With scale and deployment in the CSP market, there's certainly potential for jobs and domestic local content in the US as the market expands. So in summary, the publication that I've mentioned is in review and will be published shortly. But some of the major results, I'll just reiterate, the heliostat supply chain is in the world, at least, is fairly, it's composed of plentiful commodity materials, apart from things like mirrors. So there are only very few large suppliers of mirrors, for example, in the world. The US domestic capabilities could be leveraged to be able to meet steel and commodities perspectives if those markets have enough demand associated with it. And again, in terms of job impact, if, for example, we could get to a scale of 100 heliostat fields being deployed in the US, you could be, we estimate at least 10,000 jobs in steel and the glass industry separately. In terms of some of the uses and impacts of this type of analysis, of course, it leads to and needs further detailed analysis on different designs, on different suppliers, on understanding really manufacturing capacities, both in the US and abroad. And as mentioned at the beginning, this type of analysis feeds into the Heliocon advanced manufacturing task and also the roadmap going into the future as well. Thank you so much. Great, Rebecca, that's me.
Great, thank you. So now we have plenty of time for questions. So you can either post them in the chat or ask them aloud. And let me see. It looks like Alex has something in the chat here. Alex, do you want to speak to your comment here or your question?
Yeah, thanks for your patience. I had to unmute myself. Thanks very much for a great talk, Parthiv. I appreciate it. One of my questions was just on the installed cost calculations on slide 12.
Yep, great.
Great, thank you. So the observation that I've had from looking at this is that if we compare the total installed heliostat field cost, there's a savings of about 43 million if we go from the default heliostat to the advanced heliostat. But then the total installed costs go from 498 to 371. Right. So there's about there's a lot more that's baked into those installed costs that are now outside the heliostat field. I was wondering if you had any commentary on some of those other sources.
That's a great question, Alex. And so the important thing is that because this is built in SAM, we did analysis to show what the difference would be when this CapEx reduces. But when this CapEx reduces due to indirect and direct EPC and contingency costs, that has an effect on the overall plant cost. So based on the financials and the structuring of how SAM utilizes the cost levers, right? So the cost lever in this case is the cost of the heliostat field. You're right. There are some other aspects which are then impacted, not just a straight reduction in 47 million or so. There are other effects like some of the EPC and direct and indirect effects, which are then taken into account in the SAM case to be able to get to these levelized costs of electricity. Great question. Yeah, great question.
Okay, thank you.
And also in the chat here, I see Greg wants to clarify your LCOE numbers and estimates are just for the heliostat field and not for the total CSP power plant. Is that correct?
It's the impact of the field on the total. So for example, it is a full field plus tower plus storage. So for example, it's the full CSP field like a Crescent Dunes, for example, and then you use the lever of changing the dollar per meter squared in the installed cost field side to be able to then impact. So effectively the same field, what would the cost impact on the LCOE be if you could realize a $137 million field or even $107 million field? Great question, Greg.
Does anyone else have questions for Parthiv?
Yeah, this is Chad. I have a question.
Yeah, hey Chad. Yeah.
Hi. If you could go back a couple slides to one where you're showing the cost of tooling as a function of manufacturing volume. Oh, there it is. Great. Yeah. So it looks like this was for the run that you did on the SunRing, correct?
Correct, but only for this specific component. So each specific component has cost curves like this.
Okay, so like my question is about mass manufacturing, and we talk about manufacturing at scale. Like based off this study, would you say that a single large plant provides enough demand for heliostat parts that it would qualify as mass manufacturing? Or is there even more cost reductions possible if you were to know that you were going to do multiple plants, let's say?
Absolutely.
Or you knew that there was a good pipeline coming for the next 10
Absolutely.
years.
So, for example, even one field for a region or a locality can be considered large manufacturing, but absolutely you want to have multiple of these coming online so that one area or one manufacturer is not the only one who has the knowledge of this. So this is the assumption that a established manufacturer can take a piece like this based on the stamping produced and then get to higher volumes and lower costs. But depending on the process used, so for example, stamping or roll forming, you could even get much lower costs. And so absolutely, Chad, you're right. You need to have a consistent pipeline for manufacturers to be able to build and supply parts, but also for those types of learnings to be able to transfer from one field and one country to the next as well. But I would say that one large field is enough to give, let's say, 2 years of manufacturing production capability, but you wouldn't build a single new plant just for that. You wouldn't build a manufacturing plant just dedicated to heliostat components. You would be contracting with existing manufacturers to say, how much of your capacity can be used? Oh, we need to make, let's say, this specific part. We want to make 80,000 of this specific part. And so you would be able to utilize the machines of that shop to be able to produce 80,000. But for one plant, it's unlikely that you would build a manufacturing facility, but you would build an assembly facility. So for example, here, this specific case assumed one assembly line facility adjacent to the solar field. Now, if you're building more than one field, you would want to build multiple assembly facilities, which would then reduce the amount of time for building the fields. So for example, we know that SBP design with the perspective of multiple fields, same for solar dynamics, so that you can take equipment from one site and even shift it to another site, to another assembly site. Yeah, great question, Chad.
Yeah, thank you.
Is anyone else's hand up? I'm not sure if I can see.
No, I think just Chad from his question before. Yeah, we have
Great.
time for a few more questions if anyone has some. Check the chat, see if there's anything else there.
What is this about? Alex?
Rebecca, I've got one if no one else.
Yeah, go ahead.
So Parthiv, you broke out the cost of both the SBP and the advanced heliostat into, I want to say, over a dozen, individual components. Does the pathway to bring the cost down to 75 or 50 or any other number per meter squared, does it look like a pretty proportional reduction in all of those, or kind of a leaps and bounds improvement in a few areas?
Yeah, great question. So I know Alex is also on, and perhaps Jeremy is also on, but not every area is going to reduce proportionately, because, so for example, if you look at either design or any design, the amount of material is always going to be a constraining sort of minimum. You can't have a zero cost have, let's say, steel at zero cost, right?
Sure.
But things like drives, things like mirrors, you can apply supply chain improvements, but also things like a much better negotiated contracts. So for example, the current fields on the Dubai electric and water plant, which is a huge field, right? 600 megawatts parabolic trough, 100 megawatts of Heliostat. We know through the discussions with the developers, for example, that these types of components like the mirrors, like the drives, have had significant supply chain pressure and procurement pressure to be able to produce those. So there are some non-linearities. You're absolutely right. So for example, things like unless you used thinner mirrors, for example, right, you're going to be again limited by that cost of mirrors. Let's say in this case, where is it? This 15.88, that can only go down a certain amount if you're using 4mm glass. If you are able to have a lot more volume, maybe it'll keep producing going down. But of course, you're going to be hit with today's issues on transport as well. So there are some non-linear areas to look at as well. Great question.
Thanks, Parthiv. Great talk.
Thank you. Thanks, Dan.
So yeah, probably time for one or two final questions if anyone has them. All right. With that, Parthiv, do you want to go ahead and navigate to your last slide? So,
Thanks so much,
yes.
Rebecca.
Yeah, thank you. Yeah, thanks, Parthiv, for a really nice talk. So more from our Heliocon seminar series. As mentioned in previous emails, you can find these seminars on our NREL YouTube channel. I have the link here. We're a little bit behind on posting those. I think there's the last 3 or so that are not up there yet, but they will be soon. And the slides are also available on this Drive link from all our past presentations. So I'll post the ones from this one up today. And if you want to subscribe to the seminar series, if you're not on the list already, to get emails directly about the seminars or other sort of workshops or webinars that we put on, feel free to contact this email. Or if you have any students or colleagues who you think would like to be included, have them reach out to us and we're happy to add them to our list. And our next seminar will be at the end of this month, June 29th. So another talk from our ASTRI partners in Australia. This one will be on soiling losses for concentrating solar power prediction, assessment, and mitigation by Dr. Michael Collette from QUT. And so that'll be Wednesday, June 29th, 3 to 4 Mountain Time to make the time zone a little easier on our friends in Australia. And so hopefully you can tune in for that one as well. And yeah, if you have any questions on the seminar series or anything related to research, training, education, feel free to reach out to me. My email's in the meeting invite. Thanks, everyone.
Thanks, everyone.